Today, I would like to introduce Jeff Amstutz, who is with NVIDIA right now. He used to be with the Intel Osprey team, and he is now the chair of the Khronos Inari working group and is going to tell us all about this great new scientific visualization API.
Great. Thanks, Bill. Really happy to be here. Happy to talk about Inari and about various use cases and needs of the visualization community. It's one community that's near and dear to my heart. As I've worked on Osprey in the past and now working on the same problems at NVIDIA, there's a lot of interesting problems that need to be solved when doing 3D visualization. So without further ado, I'm going to share my screen to show some slides. And okay, let me know when you can see my screen. I will say that I think I actually can. Is this?
We see the presentation screen.
Yeah.
Yeah.
Is it actually okay if I stay in this screen? Because I just realized I won't be able to see what slides come next. Is this big enough for folks to read? Or would you really prefer the presentation mode?
This looks okay, except I think that the bottom portion of your first slide is, at least to me, a little bit covered. Well,
Okay.
actually, no, it's fine. It's fine.
Okay. Okay. Yeah, because I just want to make sure that I'll just preface up front. These are slides that I gave as a pre-recorded talk at GTC last fall that you can find online. We can, of course, send links to that if people would like to watch that. What I'd like to do here is do a hybrid of some of the talking through some of these, but to have it be interactive, where if there are questions or more of the why behind some of the API design choices, I really want to engage with folks. And then also I'll show a little bit of live demo of some just apps I've been working with locally as I've been developing our backend. So without further ado, I'll get started with this. Please, at any point, please speak up at any time. I'd love to hear from you. And I'm on a separate desktop from where Zoom is. So if you use the raise hand feature, I won't see it. So anyway, the first thing to talk about is Inari is a Khronos API standard. And if you're not familiar with Khronos, they're an open standards consortium where companies, nonprofits, academia come together to create industry standards that have a nice, safe IP zone for developing APIs and standards that are useful across industry and academia. And so Khronos was a natural fit when we wanted to come together and create a 3D visualization API. And so the timeline that we have been on as a standard is we started, there's this thing called the Solar Consortium, which was ray tracing for simulation. And in that group, there was a bunch of interest to say, hey, we also do ray tracing for Viz, which is a very natural thing. And we want to create a standard. So back in May of 2019, the initial idea of pursuing a standard began, and that moved toward that November already. We had already started a Khronos exploratory group, which is really just about finding how much interest there is in industry for doing a standard, which then that following spring in 2020, you'll notice in March of 2020 is when we got started as a working group. So it was very timely for us to find COVID. But over that year and a half, basically an entirely developed standard during COVID. Last September, we released the Inari 1.0 provisional specification, which is up online, and you can go and read it and find it. We also published our SDK up on GitHub. Anyway, that was a big monumental moment for us because in those very trying times, it was very difficult for a lot of us. We were still able to get that out. So that was very exciting. And so September was when it was under IP review. The actual release of it was in November. So just a few months ago, we went public with the specification. And so where we're sitting at now is polishing conformance test suite development, SDK development, to bring Inari to the official 1.0 release that will include everything, not just the specification itself. So then, of course, we have this weird name called Inari, and we want to know what problem does it address? And it's actually supposed to be an acronym. Turns out naming things is hard. And a lot of good names are already taken. So it's really the analytic rendering interface, which came out of this need of we want to do analytics, like visual analytics, and we want to interface to renderers. And that's just the name we got. So it's the one we have. But the problem it solves is we have applications that want to do visualization as a part of their workflow. So a couple of applications that have been involved with the working group that are pretty common is ParaView, Visit, VMD. And they've got a bunch of rendering engines where you can give them 3D data and they give you a frame back. The problem, though, is that every application then has to do n different individual integrations with these rendering engines. And so what you end up with is maybe one or a couple of rendering engines get integrated in these apps, and then it just stops after that because it's just too much software burden. And so this is a very non-scalable, non-desirable problem that gets faced. So what Inari solves is you talk to a generic rendering interface, and that interface forwards all that information from the app to underlying rendering engine, and of course gets the results back in a standard way. Because it turns out at the level of the Inari API, there's not a ton of innovation. Apps are going to do innovative things, and rendering engines can do innovative things, maybe fast, high quality, all of the above, cool hardware. But the actual like getting these things to talk to each other is where it's not like Osprey, Radeon per render, and like the Cycles rendering engine, that their unique contribution to the world is the API they expose. And so that's what Inari is trying to take out is let's all speak the same API because this isn't where we need to be fighting each other. And so what we've designed for is an API that can work equally well in all types of rendering contexts. So offline rendering, interactive rendering, and real-time rendering. The difference between interactive and real-time being interactive is where it's tolerably human in the loop, where real-time is like a hard constraint type environment. But Inari is fit for all of those. And we really designed it to kind of get out of the way. So if a rendering engine has a cool, unique feature that it wants to expose as an extension, we're built for that. That's very much built into the API design choices. And then, of course, on the application side, we don't want the application having to get too narrowed into a particular rendering engine. And so getting those things to meet is the difficult part, but actually Inari not being in the way of either side is the goal. And then we also want to leave it open for rendering engines and applications to optimize in different ways. So just because you can interface to any rendering engine doesn't necessarily mean that all rendering engines will work equally effectively in your application. The whole point of Inari is you shouldn't have to write new software to at least be able to do that. And so different implementations will make different choices, and that's by design. We're not trying to create a single renderer. We're just trying to create a single interface to any number of renderers. So the way the stack looks is you got an application, and in it some type of scene representation. So you have objects like geometries or volumes, and they're grouped together, particular material parameters, etc. And that information gets shared with the Inari API, which then forwards that information on to things like renderers like Osprey or Radeon per render, VisRTX. And then once you're in the rendering engine, all the stuff below it is implementation detail. So there's nothing that Inari says that you have to have like an OpenGL context or something like that. Of course, we can have extensions to let you do interoperability with those things, but that's different than assuming they exist. So if you have a pure CPU implementation, great. If you have an optics accelerated one for NVIDIA GPUs like VisRTX, great. So that it's actually a feature that you're not at this level of abstraction that Inari is, that you're worrying about all those lower level details. And so, there's different levels of abstraction, and we'll talk about later about how these all get divided, because what ends up happening is if you write an application and you do all of this yourself, you may end up having subsystems in your application that represent each one of these. And what we're imploring folks to do with Inari is to, even if you both implement the API and use the API in your software ecosystem, that there's still benefit to doing that. So I'll skip ahead here. Like what what are some of the core tenets of what the API looks like. It's C99, but we have C++ and other language bindings in our SDK to bring back convenience. But the core of it is C99 for portability. It's built around the notion of a common front-end library. So you link one library, the SDK, and then the SDK is the one responsible for doing the mechanics of loading a backend that's going to listen to all of those API calls that you're making. And so, yeah, there's an SDK that brings a bunch of quality of life and debugging tools. We have some cool stuff there that we've been working on already to be able to do like API tracing and debugging that way. Influenced a lot by Vulkan choices, not necessarily an API complexity, but the idea of having a debug layer, that kind of stuff. And what's really cool, and I'll show some slides to illustrate this, is this one single API is equally applicable to single machine, single GPU, single CPU rendering, all the way up to rendering on clusters. And so this will show that. So this is probably the most common setup. You have a single application, basically a single process that in that process is talking to the Inari API, talking to an engine running on hardware. There's a cool setup called offload rendering that is, you have a single process talking to a single Inari API that's then forwarding rendering calls to multiple machines, maybe over MPI. And this lets you do transparent image parallel scaling without the application ever needing to think about that problem at all, because it just thinks it's talking to a local Inari instance. And then the really cool one is where you get like an existing MPI distributed simulation, and you want to do like in situ visualization where each rank is talking to the Inari API, and when they all say render a frame together, one of the machines then has the rendered image of all of the data on all of the nodes. And so that's a setup commonly found. A lot of the big national supercomputing centers and stuff, they're big distributed simulations. The point being is we don't have to change the API itself to be allowable to be to meet these semantics. Of course, like there's different setups that are required for applications to take advantage of this, but you actually aren't calling any different functions in each three of these environments, which is super exciting. Okay, so next, I'll pause here real quick. Does anybody have any questions so far?
I had a question, and maybe you'll get to this. Is it does Inari cover purely the rendering side of things, or does it support any of the other things like camera motion or something like that?
Yeah, so I'll go back to this stack. It's really focused. It's a render graph API, and so the reason we avoided doing generic scene graph operations is because a lot of that is really dependent on the domain. And so once you boil down something to say, I have a frame I actually want to make pixels with, by the time you get to that point, that's where Inari then takes it from there. But things like camera pathing or just non-rendering operations to a scene graph, like different kinds of transformations you make, like I'm thinking like USD type, you can really scale up the complexity on the scene graph side. It's just a huge, massive problem. We don't want to not solve that problem. It's just that would be a separate thing to go after. Does that make sense? Cool. All right. Any other questions? All right. So the core of the API is built around a concept of an Inari device, which an Inari device is a software device. So you logically are have a software system that's using the API talking to another software system that may or may not use more than one hardware device underneath it. But of course, that's implementation detail. And so with that, in every API call, you're going to see the first parameter is always this device thing, which is that's a concrete instance of the rendering engine that I'm talking to. when I'm making my API calls. So what this does is then lets you privately have separate conversations with your application to multiple live rendering systems, and they won't interfere with each other. So the notion of extensions is that these are things that are optional. So if you're a compliant implementation, that's all the core features, and then there are some extensions that we have ways of classifying those. But all extensions are additional things, which sounds straightforward, but we have like different object subtypes. You'll see that there are different parameters you can parameterize an object with. And so an extension might say, hey, we listen to other parameters than the ones that are standard. And in rare cases, you can get more complex things like API functions that like an implementation may have you actually link to see API calls into your application. But we won't get too far ahead into that. The way we classify extensions there are core extensions and vendor extensions. So a core extension just says this exists in the specification. It's just a non-required feature. And then a vendor extension is you need to go read that vendor's documentation to find out like what it is, how it works. And the idea is vendor extensions are where core extensions get prototyped, and then core extensions. So a vendor extension becomes a core extension if it's good and there's reason to believe more than one vendor would implement it. A core extension starts as a vendor extension that has been deemed good, and we think if everyone wants to implement a core extension, then that just becomes a core feature. So that's our upgrade path. The cool thing is the Inari API assumes all of these exist, and the notion of an extension from the API perspective is the same. We're just literally talking about the specification at that point, not the mechanics of interacting with an extension. And the way that's done is there's just a simple test. You ask your device, hey, do you implement this extension or not? And then you go from there. So it's good to get this out of the way quick. Error handling is through a callback. And so you attach to your device a callback that gets invoked whenever anything from a debug message all the way to a fatal error has occurred. And then this just empowers you, the application writer, of what do you do with this information? Where are you going to plumb message output? How are you going to react differently to different types of severities of errors? Cool. So objects are the core of what you're interacting with in the API. And so an object has a bunch of properties that we characterize them as. They're opaque handles. So you create an object and you can use that through the API, but it's not like it's a struct or anything that you're directly manipulating. It can take parameters. Objects can publish properties. We'll talk about those. And then it has reference counted semantics for how their lifetime is managed. And so objects represent everything you would think of when you're rendering a 3D scene, from your geometries, your volumes, materials, lights, your camera, all your instancing. Just everything's an object that shares these properties, these ways that we characterize them. So objects are created with a bunch of functions that are already new. So if I want to create a camera, I can create a camera from a particular device, and I want the perspective camera. And then some objects don't have a subtype. So like a world is just a world. And we use, maybe we can talk through the reference counting. It's not super complicated, but every time you get an object from the API, you have at least a ref count of 1 that's public. And then you can use release or retain to increase or decrease that ref count. And once it reaches 0, you're no longer allowed to use that handle through the API. And so the reason that is because you can have internal references. So for instance, if I have a world and I have that set on a particular frame object, that's my top level object, I could release the world, but the frame's still pointing to it. So the world's going to stay around until that frame doesn't need it anymore. Parameters, there's a generic way you set parameters, and that's through an ANARI set parameter. It's really on a particular object, you have a named parameter, and then the value, which is set from a fixed enum collection of types that we understand through the API. It's a pretty long list, so it's difficult to imagine there's something you'd want to set that isn't on that list. but yeah, it's just name value pairs for setting parameters. One key feature, this is about the world of extensions, is if you set a parameter on an object that it doesn't understand, that device might emit a warning saying, hey, you set this parameter, but I'm not going to do anything with it. But it's definitely not fatal. And that's a good thing, because I could have an application that I've used, and maybe I use a vendor extension. What I don't want to have to do is have conditional code in my application that if this extension isn't implemented, that maybe there's this extra parameter that it listens to. If you load a device backend that doesn't implement it, we want your applications to still function, even if it doesn't maybe do exactly what you want. We'd rather it not be a fatal thing requiring conditional code all over the place. So this becomes really, really handy. So an set parameter looks pretty straightforward. I create like a camera. I said it's where it is in the world and its aspect ratio. The key though is these parameters are transactional in nature, and what that means is you set a bunch of parameters, but they aren't used by the object until we've committed those parameters, and that's with an ANARI commit. So what that does is if you have an object that requires some set of parameters to be valid, like for instance, if I have a triangle mesh and I need the vertices for a triangle mesh to have any chance at defining a valid triangle mesh, I want to be able to transition an object from one valid state to another valid state all at once. And so the commit lets you do that instead of always committing after every parameter set. And so the way we visualize this concept is you can think of, I have a table of values that have been staged with set param, and then when you call commit, they become live, and the next frame will then respect the values that you committed. So the one thing that is unique to setting parameters is that arrays themselves are objects. So parameters are single values, which can include handles. So you can set a handle on an object. That's a type of parameter. But arrays, they're standalone objects because they express multiple things that all wrap together. One is the type of elements, the number of elements, and then the ownership of the memory associated with it. And with that, we have shared arrays. So an ANARI object is just looking at memory in your application. We have captured arrays, where you pass the pointer and a deletion function. So when ANARI is done with that array, it will call your deleter to free that memory. And then, of course, there's managed arrays where you just create an array and then you map a pointer to it, write to it, and then unmap it. So these once you have an array, you privately are concerned with that problem, and then where you can put an array is then just that issue of ownership is not then an issue anywhere else in the API. So properties are the inverse of parameters. Properties are where an object can say, here are values that I want an application to understand. So for instance, on the ANARI world, I might ask, give me your bounding box. Specifically, these are not the same as parameters because based on implementation choices that implementers might make, especially in distributed rendering contexts, it may be really expensive to basically ask the API to read back every value you've set. It's just not a really great design pattern, but properties are just unique things that the implementation can't have. So for instance, if I set a value on an object, the application can keep that value anywhere. If I set the number of samples on my renderer I want to take per frame, I don't need the API to tell me that. But I might ask, because I can't, let's say, compute the bounding box that the implementation's using on a particular object, but it will have to. I can say, hey, give me the bounds, and you can ask that. So there's specific lists of parameters and properties that each object has. But it behaves very similarly, just instead of an input pointer with an input type, it's just an output. So it behaves very similarly. Yeah, here's an example of, for a particular world object, I have the bounds property. I know it's a float32 box 3, and that's how that works. So with that, there's a bunch of different types. They're all different handles. Like I said, cameras, renderers, groups, instances. And there's a lot of them, but it is a fixed list because the different actors that go into rendering a frame are relatively fixed, even though we can have a bunch of different subtypes of each of these. Like for instance, an Inari geometry just represents in 3D space something that's basically intersectable or rasterizable. But there's a bunch of ways you can do that. You can express that. So with that, this is what's more interesting, is to look at what's the hierarchy that I create of these and how do I relate them together. Our frame is our top level object. So the reason we have a notion of the frame is the top is because any handle can go into more than one parent. So for instance, I could create an animation of multiple frames that have sub pieces of like a static part of the world, but maybe are a volume animation. Each volume time step is separate. I could string those together if I want, and then just play them, and I wouldn't replicate anything I wouldn't have to. So if I had like a static, like if I'm doing a wind tunnel over a car, I could have the same car instance that has all the car stuff in it, and then just be swapping out volumes to play the time series. That's one way you could implement that. It's not the only way. But our frame is the one thing that you can't share with anything else. Like the actual frame setup is something unique to rendering that frame. This would be the frame buffer, and then of course the objects we're going to use to populate that frame buffer. The world is basically everything that contains things that could show up when rendered. I'll show an example of what render encapsulates. It's really the algorithm plus the parameterization of that algorithm that you're using to generate the pixels. And so what else? Inari frame, I talked about it being the top level object. This is remember, every object is just set parameters and commits for the most part. You create it, set some parameters, and commit it. When it comes to actually rendering a frame, it really is this simple. You call Inari render frame. And the big key here is that it's asynchronous. And so every other API call is synchronous from the perspective of the caller. There might be asynchronous stuff going on in the implementation, but the caller is assuming that those are all in order, where render frame will just start the frame, and you could actually render frame a bunch of times. And until you wait on that frame, it may or may not, of course, be done by the time you want to map it. I believe Inari map frame assumes there's an implicit wait in it, but what's desirable is you might want to start a frame, and if it's really, really expensive, like this is something Paraview struggled with for a long time, where I want to start a frame, but I want to keep making sure the UI is live. I don't want to block my whole application because maybe I can only get one frame a second out of my rendering engine. That's what this lets you do, is it immediately returns control as soon as possible back to the caller of Inari render frame to let you go do other things like render your UI. So this example just renders a frame, immediately waits on it, maps it out, writes it to a PNG.
I have a question.
Yeah, go for it.
So what happens if you do other operations on the frame before you wait for it? After you start rendering the frame, you start doing some other operation like set parameter on the frame, and then you wait for it.
Yeah, so that's legal. I guess the asynchronous semantics is from the perspective of the expected execution behavior, not the validity of API. So there's no API that's illegal to call while a frame's happening. What will happen though is they might implicitly synchronize. So for instance, here's one. If I have a frame, and let's say I have a triangle mesh with vertices, and I wanted to map that array because I wanted to write new vertex positions because maybe it's animating. And so that map of that array should block until the frame is completed enough that it knows that it no longer needs those vertices. And so what this does is you could say render frame and then immediately map that vertex array, and you will only get out of that map operation as soon as your implementation lets you. So a very unsophisticated implementation, those will all just be synchronous calls, so it wouldn't matter. A very sophisticated one would say, maybe I'll give you a staging buffer to those vertices that you can now start writing in while I'm still chewing on the frame, on the pixels. Does that make sense?
Yeah.
Cool. Yep. And then, yeah, your frame is what holds your frame buffer output, multiple channels. So you can have like your color buffer, depth buffer. You can either, there's an extension that allows you to get things like albedo or normals, anything you would want to do for post-processing that image. So I promised to talk a little bit about the renderer. Here's an example that I was writing a little optics implementations now turning into the next generation of VizRTX, but the time I made this, I just had little 3 renderers, a raycast renderer, an AO renderer, and a path tracer. The only difference between these frames is the renderer object used that's attached to the frame. So you can get wildly different algorithms all in one implementation. So for instance, there's no standard set of renderers right now. I didn't mention it in these slides, but there's ways you can actually ask your implementation, like what renderers do you implement and what are their parameters? But the point being is you could have like a Vulkan renderer that exposes multiple different, a Vulkan device that has multiple different renderers in it that have different trade-offs. So for instance, on the left side, this is the cheapest to render. This is super, super fast, and they get progressively more expensive from left to right. But you shouldn't be having to do anything other than change the renderer object out to get those different looks. Just some API basics, just zooming in here. Surface is a really interesting one. A surface combines 2 things, a geometry, so the actual 3D representation of it, and then the material, and your material is going to take information from the mesh and apply appearance to it. And when they are combined, you get what the notion of an Inari surface is. So a surface just points to these 2 objects. These are the heavier weight things. And with that, I'll jump over to a little bit of demo. I think I need to share my whole desktop this time. So here's a little sample application I've just been messing around with Inari and Deer MGUI, if you're familiar with that. Are you all able to see this application?
It's good here.
Cool. What this is this is running VizRTX, which is the forthcoming open source implementation of Inari from NVIDIA that I've been working on. This just runs VTKM, which is a data filtering library from Kitware. It's been really cool, fun to work with. This is what they call the Tangle source. This is just me experimenting with VTKM. But what's real cool is this is all just done in real time. So what I'm doing here is rerunning a VTKM isosurface contour pipeline or filter, and then extracting all the triangles and creating all the Inari objects and putting them in an Inari frame. And I have a separate kind of class that's managing this viewport. That's this camera that's listening to mouse stuff, and the frame itself that's getting displayed. It's just a little kind of proof of concept app. But the point being is this is all completely agnostic to VizRTX. So all of the code that's doing all this this stuff, I've got all kinds of little widgets in here that do things. All of this has nothing to do with VizRTX. I could load up Intel's Osprey. I could load up the little example device that's inside the SDK. That's really, really slow. But the point is it can talk to all of those, and this app functions the same as long as those implementations are complete. We have very scattered completeness of the API right now in our implementations, but this is the kind of stuff Inari lets you do, is not only do this fast interactive rendering as you would expect. That would almost be assumed in something like this. What's cool is if I wanted to go use Osprey, I could make this application, create a second viewport like alongside, and be viewing them right next to each other. Or maybe I've developed my application and I want my users that maybe don't have an NVIDIA GPU to still use my application. Well, great. Go use Radeon ProRender on your AMD GPU or use Intel Osprey on your CPU. Like the point is your application no longer needs to ever think about what is it running on. And what's cool is this isn't even GL. This is straight up ray tracing. You can actually see all that ray tracing noise right there. So all of those details are encapsulated by the Inari backend. Yeah.
I have a question.
Yeah, go for it.
Is anybody working on a WebGL or WebGPU implementation, perhaps compiling the C code to WASM with Emscripten?
Yeah, so that's a really good question, because there's a couple of things that I'm not terribly knowledgeable about WebGPU from a detailed perspective. One thing is the Inari API is a C99 API. So as soon as you expose something like that to JavaScript or just any of the web stack inside a browser, I wouldn't start with using the web stack to implement a C API just to go back to the web. I would think as soon as you've got Inari in your browser, I would personally say choose the native APIs there. That being said, I'm not an expert on that stuff, so that'd be a really interesting discussion because I have a lot to be educated on as well. Yeah, go ahead.
Another question I have, I'm thinking about an application that supports rendering locally on the user's machine and then also rendering on a cluster, for example. And from your presentation, I get an idea of how the API could be used to set up the content of what's going to be rendered, and then there would be separate rendering objects for maybe for the local renderer and the cluster-based renderer. But could you give some idea of how the application might go about deciding about certain details of the rendering that are expensive enough that they should be left off in the desktop version but enabled in the cluster version?
Yeah, so a couple of things there. One is Inari doesn't, basically the assumed like performance quality trade-offs that your application will observe. I don't know if we have any notion of detecting that programmatically. What this really would be is I start up my application, and as soon as I start talking to the Inari API, it's really making the choice of what implementation do I load and then start using, is I think the core part of that question, where once you're talking to an Inari device, like for instance, this application is talking to VizRTX. I actually don't think it would work right now with the state of my machine I have, but I could just run it with the example device. I could run it with an MPI enabled one like Osprey. If you're wanting to real time like jump between a local machine and cluster, that is something that is the Inari API just says you're choosing which Inari device am I using, and it's not singular. It's you create an Inari device, then all of your you express your whole scene as from that Inari device. So that would be your application would probably need to be implemented specifically for Inari devices that are going to do offloading to a cluster, and then have your application like participate in setting that up correctly and everything. I think it's kind of both. Your application has to, like, let me just talk about MPI because that's what I know. For instance, like if you're going to run an MPI application on a cluster, someone has to MPI run something or launch your job. Like there are mechanics there that have to be solved that Inari doesn't. It's orthogonal to the Inari API. And what I mean by that is this feature of running on a cluster with the API came from Osprey, really. And the way Osprey did it was you initialize Osprey, and if you initialized it in an MPI run context, we're going to load our implementation that knows how to divide the image into smaller pieces and then composite that back together on your one process that loaded this. That still required a user to like MPI run your application, or maybe do a split launch with your application, your interactive piece, and then all of the workers running on all the nodes. All that stuff is still, it's like Inari doesn't just say, I can do that for free. Like that requires some setup. That being said, at least once you start talking to a device that is doing all that distribution, you're not doing anything once you have that device set up. But it's not a ton of lines of code, but it's just you can't automatically just, like, there's no way if you're running on a cluster somewhere, like if I'm at TAC or at Oak Ridge or something, I can't just say, oh, my application suddenly just knows how to launch a job at TAC. I'd have to be involved with that process.
So those would be extensions that would be implemented by the MPI renderer, and so the application would do a lot of setup that would be common to that renderer and the other renderer. But then when the user chooses to do it on the cluster, they would be calling other extensions.
So potentially, let me just show a few lines of code for what I'm talking about. It's really these two initial objects. So an Inari library is really, it's like we're DL opening a library on the file system to say, I'm going to go find a library that has device implementations in it. And so, for instance, this is hard coded right here to use VizRTX because it's my little app. If I wanted this to be completely like dynamic, this could be like an environment variable or a command line option to say, hey, go look for this Inari implementation. My application also could go take a fixed list of these and just load a bunch of libraries. But then the most important piece is, what's the Inari device that we end up basically building the rest of the application on? And so from a library, we can say, give me your device from that I've dynamically loaded. Give me an instance of this rendering engine that then I'm going to use. So the decision then about, is this an MPI enabled device, is my collection of Inari libraries, does one of them implement this? Which is, me as a developer of an application, I know up front. For instance, if I'm loading Osprey, I have looked at Osprey's vendor documentation to say, hey, we implement a local renderer, a offload renderer, and a distributed renderer. All of those are Inari devices. And so with that, you would then also have to look at Osprey's implementation to say, you need to run the Osprey MPI worker on all of my compute nodes. And maybe the only place in my application here would be, if I have chosen the MPI device, maybe there's multiple ways you do this. That setup would be here, but the point is, as soon as this is set up to like be talking in the right MPI world and all of that, once I've done that, this is all identical, like the rest of the application. So I can't, no one can make an API that abstracts you from running on one machine versus N machines without you being involved on how do I talk to those N machines. But that's now like just you're just looking at the parameters on that vendor's device to configure that. Hopefully all that makes sense.
Yes, thanks.
Yeah.
I have a question.
Yep.
Can we use custom shaders on Anari?
So this is an interesting topic for a couple of reasons. One is, the answer is both yes and no. Here, the answer yes is, it depends on what you mean by shader. So if the material system, the way it works, and I didn't explain how this works, is, let's see if I can find something real fast. Okay, so the way the core, this is the core feature sets. This is what you have to implement to be compliant. You create an Inari material, and then you set parameters on that material. So for instance, if I had if I want to use this vertex color array, the way I would use that is I would say ANARI set parameter, doing this live coding here, device material, the color input to this matte material needs to come from there's a fixed set of attributes on a geometry, and it needs to come from the color attribute. And so what this does is I could make, there's a bunch of different attributes you can populate, and you can plug them into any material input. So for instance, if I had a PBR material, I could map this to like roughness or something like that. If you're trying to do that kind of programmability at runtime, that's basically you doing this really coarse level shading network type operation. If you're wanting to write GLSL, that's where the answer is yes, if there's a vendor extension that lets you take GLSL as a string and plumb it through a material. So I might have an extension parameter or extension that has a material type that's custom called like custom GLSL or something like that. And then that device implementation needs to understand the GLSL you hand it. So even that's not a fixed thing. It could be if it's a GL implementation, you can say, here's a fragment shader, but even then you need to know the names of all your shader inputs and all that stuff. So there'd have to be a degree of handshaking there. But the massive assumption there is that you're assuming GLSL was involved at all in the back end. Actually, none of the current implementations that are being stood up by vendors, nobody's using GL yet. We had an exploratory one to prove that it would work with GL. But there's just no assumption that GL is involved at all, or anything that understands GLSL. So you're squarely in your vendor extension land that someone even lets you and even understands GLSL. The middle ground, so we have the coarse one, which is, yes, you can do this kind of wiring up at runtime. That has to be implementable by your devices. There's also like the real custom, I'm writing HLSL, GLSL, whatever it is. The middle ground is shading networks like you would find in Blender, where I can create nodes and then wire up those nodes, and maybe your backend compiles that down to GLSL or whatever it needs. That's something that we'll look forward to in the Inari API eventually. But so that's why the answer is yes and no. Sure, like I could write a device implementation because we can express strings. Like notice this is a string. As soon as you can get strings as parameters, it could be an entire GLSL shader. But yeah, you have to be participating in the implementation details of that device backend for that to be anything you could make sense of.
Thank you.
Yep.
Do you know what the time frame might be for looking into shader networks like in Blender?
It's really as soon as there's a device implementation that implements it. So I'll be interested in MDL eventually. One thing because I don't have enough time in the world, one thing I'd love to do is to see cycles be put behind the Inari API, because I've looked at the cycles implementation and understand it enough. I've played with it standalone outside of Blender. I've played with it enough to know that like I could totally express this as Inari objects, like a node. But it really, because these standards are done by volunteerism, essentially, it's really when there isn't like a funded project right now that someone's doing that. It's really as soon as a renderer that has that and wants to say, I want my users to use my shading networks through the Inari API, that's when it'll get seriously looked at. So I don't have a good answer on that.
No, that makes sense.
Yeah.
Thanks, Jeff. I think you were trying to do a demo there.
Oh yeah. Yeah, this is just a different app of that I wrote. This little diffuse, I even forget what DLAF stands for. It's just a little fun fractal type code, and the whole point being is like when you interact with objects in the Inari API, really the mechanics of what has to change in my scene is pure implementation detail, which is huge for the application. So for instance, these particles I generated, when I change the radius on the geometry, underneath the hood in VisRTX, I have to rebuild the bottom level acceleration structure over the geometry. Then I have to rebuild the top level acceleration structure over the instances in the scene. And I'm doing that every time I move this. If you write the renderer yourself, it's really easy to blur the lines of, I have my app that's manipulating the scene, and it happens to know exactly what the BVH looks like, what all the object layout is. And that's what we're keeping out. So yes, writing code that lets you resize a radius on spheres is not terribly exciting. The super exciting part is this code has no idea what structurally has to change in the implementation to have this update. All it does is say, I want a different radius on this geometry. And the implementation behind the Inari API takes care of everything else. And it's doing it in real time super fast, which is great. Yeah.
In terms of the standard, what was the most difficult thing to get agreement on?
Yeah, that's a great question. The most difficult thing is probably been, this is with all standards, with dealing with things that people think is possible and think is simple, and we should just add it. So being disciplined with trying to prove to ourselves that the stuff that we're adding is both ubiquitous, usable, performant, all of those things. And so we've got to a point now where we've proved ourselves, like the way we've done materials and the plumbing from geometry attributes to the material inputs, like all that stuff was kind of in our head. And now we've proved that it works, because that's what VisRTX implements. But that's probably the strongest area of friction, is when someone says, I've kind of done this before in an isolated place, or I have enough experience to tell myself it's fine, to then call that enough justification to put it in a spec that says, for you to be compliant, everyone has to now implement it. That takes some discipline. So that's actually not even just one thing. It's just across the board. A lot of choices have to go through that filter, and that can be like emotionally difficult for folks to go through of, I have to actually prove what I'm saying, because not everyone has my life experience, et cetera.
Maybe
so were there a lot of things that had no real implementations at the time that the spec was published? Like that it was like there were some things that were just theoretically, yes, this should be doable, but no one had done it before.
So I'll say yes and no. The things that I'll say haven't been done before are just the particular like implementation choices, like the asynchronous frame stuff. Like we early on, we just wanted to say you can just launch a frame, and then every API call should just be able to know if their object is like participating in that frame or not. And if you just like map an array, that's going to be the perfect minimum time necessary. Like we were just saying that's theoretically possible. But it's not like we had an implementation that was like pounding the API in that way. And we're like, yes, we don't have a better design for performance or something. It's not like there are geometry types that no one's implemented before, or spatial fields or anything, or materials. It's really the way that they interact together. And when we're talking about latency, we're talking about like nanosecond type measurements on some of this stuff, and like scalability and all that. Like could like the Disney Moana Island scene, it's like something like 1.6 billion triangles or something like that. Could the Inari API chew through that? Well, a theoretical implementation could. That's different than assuming no one would ever operate at that scale. But we've done our homework and feel good about that stuff now.
Well,
yeah.
I had this might be a naive or silly question, but so, you said that this is spec'd out in C99. Do you think that anyone will create a kind of C++ convenience wrapper around that? Or do you think that actually there would just be no demand for that because all the C++ users are probably operating at a higher level anyway, like they're using BTK or something like that?
So spoiler alert, I already have C++ bindings to it in the SDK because I actually care about C++ way more than C. The reason to settle on C in the spec is because the surface area of the raw API definition and requirements and portability guarantees we make are easier to assert. So, for instance, I think this is the C API. The C++ bindings make this like so much nicer. Like Inari set parameter now inferring like this is a C++ bool that like anyway, like all that stuff exists in inferring Inari data type enums from C++ types, like that's in there in spades because I would really hate myself if they didn't exist.
Are you able to are you able to, I guess, save the user some of the reference counting logic as well using C++, or is that something that?
So it's something I want to get to. We had that in Osprey. Osprey was different because this device was implicit. You initialized a global device very similar to GL, and then you would say, "Here's my active context," and now your APIs are operating on that. What gets that tricky with that is then every handle has to know what device it came from. And until you sit down and try to implement like the front end API and a device implementation, you can't ask the question like, this handle, which device did you come from? Can you give me your device handle from yourself? And the problem is you have to know whose device gets to answer that question unless we all agree on a forced internal object representation. What I mean by that is technically the C API says a handle is just a 64-bit pointer, but you could stuff like an index to an internal array, object array inside your device for that. Like that's a very valid implementation. We had people doing that, meaning like it's not just an object I can dereference and now I have internal state I can grab a device from. Anyway, all this to say that I have ideas for how we could solve this. So you can get back to like my handle wrapper with destructors and constructors takes care of all that. And I know it's possible if you can solve you have to pair the device with it. And that only matters because there are places where you create arrays of handles. And now if I create an array of the handle wrapper, if it contains both the device and the object handle itself, I now have a strided array, which is fine. The Inari API lets you do strided arrays, just solvable problems that just haven't been fixed yet.
Yeah. Hey, Jeff, I had a question about you had mentioned the process by which you had extensions and then the core stuff like in the object types. And in particular, I was thinking about things like GVDB and nano, VDB and the implementations that might allow something like this. Are you working on that at VizRTX, and how would that look compared to like what's currently in the core specs?
Yeah, so the core spec, we have for volumes, we have two different things. There's the spatial field, which is the actual raw data itself. And then the volume is, you could think of as like your shader giving appearance information to one or more spatial fields. So the spatial field is where you talk about structured regular volumes, rectilinear, curvilinear, all that stuff, VDB being another. And so we only have structured regular volumes right now because that's like the one we know everyone can deal with. There's two answers to that question. One is your device implementation could decide to sparsify a structured regular grid as an implementation detail. Like before I put it on the GPU, I could just say, hey, I'm going to hand this to VDB, have it sparsify it to save memory. The second question is, what if I already have VDB and want to hand it to a device implementation? I think that's definitely coming soon. It's a matter of getting a device implementation to understand VDB natively, plumb it through the API, show that it's good, and we'd be happy to put it in the spec. Just got to get there. So yeah, hopefully that's helpful with both answers.
Another question about the 1.0 release. So right now it's to be determined, and it sounds like you guys want a really complete SDK. Does that include like Python bindings and all the other stuff that is?
Yeah, so the thing required for us to be allowed from a Khronos process perspective to get 1.0 out is the conformance test suite has to be implemented so we can declare who's conformant. Everything else is kind of nice to haves. The SDK put C++ bindings in there because I'm personally motivated to have them and I want everyone to have them, so I put them in the SDK. That being said, things like binding to Python or any other language is something we'd be hugely open to. Again, there's multiple definitions to this. It could be like if you have a system like VTK and kitware getting Inari in to replace their internal ray tracing stuff inside VTK. One answer might be that a future version of VTK just lets you load Inari implementations and then you still use VTK and its Python bindings. Of course, the flip side of that is, if I'm doing stuff in raw NumPy or whatever, then of course, yeah, we'd love to see Inari itself bound to languages like Python. There aren't, again, the volunteerism part of this means unless one of our members is personally motivated by it, it won't just happen. But we would love to see it. That'd be a great thing.
What's the timeline right now for sort of potentially compliant renderers? Like you're working on VizRTX. Is that the closest along, or what's the?
Yeah. So right now there's so Osprey's out. Osprey has its implementation. Some limitations. They're of course continuing working on it. We have a device that actually it's a USD device that's also out. And how we're using that is you can have your Inari application, take this rendering API, and then you can connect it to like an Omniverse instance. And when you're making 8 Inari calls, you're actually populating an Omniverse stage. That's a whole discussion in of itself. VizRTX, I'll put a shameless plug in here we have a webinar for Inari coming up on March 2nd. And my personal goal is to have VizRTX ready by then, in which case it'll be out on GitHub on the VizRTX repo. So we're within a couple of weeks of that. And there I'm going for mostly completeness. I don't want you to say, hey, there's this really obvious thing in the API that you just skipped. I would like to minimize those. But it's very functional already. And then Radeon per render, I'm not sure what their timeline is, but they are working on it and want to release that soon to the public. So yeah, there's an example device inside the Inari SDK. It's just a very minimal thing for the sake of like running the examples and seeing how you might implement the API. I don't think it'll ever be compliant. So hopefully in a couple of weeks, they'll at least be VizRTX and I can tell you to go use that. Yeah.
Great. We're actually a little bit over. I guess we could field a question more or two, but then we should probably wrap it up.
Okay.
Anyone have any other questions?
There's two things I'll just say real quick. One, come to the webinar on March 2nd because we're going to have a couple of talks that are in that. It'll also be recorded on YouTube. And then the second is, if you're thinking, I only want to use Inari, you should also, if you have a renderer you've implemented that does any type of 3D rendering, I really implore you to consider implementing the Inari API for both portability in the one application you wrote that renderer for, and maybe your renderer could be cool to be used in other applications. So it could be a really cool way to subdivide out your own stuff. But cool. Just wanted to throw that one in there.